Hello everyone, I am Samskruti, student of Computer-Aided Structural Engineering Master's Program, Mahindra University. As a part of our course, Infrastructure Health Monitoring, I am going to present my project topic, Energy Harvesting by Footsteps using Piezoelectric Sensors under the guidance of our professor, Dr. Visalakshi Talakoglu. These are the contents that we are going to look through today. Energy harvesting, methodology, materials required, working principle, working of model, details of rectifier circuit, model preparation, model testing, application in civil engineering, and references. Energy is an overwhelming need in the present and future because of the unconventional ways of use. Non-renewable resources are depleting at a faster rate. So we need more alternatives and research of renewable energy. What is energy harvesting? The process by which energy is derived from external sources and converted into usable form is called energy harvesting. There are many renewable energy resources like wind, solar, hydro, vibrations. We are going to look at one such technique today. Why is energy harvesting important? Energy harvesting is important because it is mainly maintenance free and environmental friendly. It also provides a new means for powering electronics without conventional power. It also eliminates the need for frequent replacement of batteries and also opens new applications in remote locations like underwater and areas which are difficult to access. The methodology followed is as follows. Study the basics of piezoelectric sensors, understanding the requirements of piezoelectric energy harnessing, and designing the footboard model. The materials required for the model are piezo sensor, coaxial wires, a rectifier circuit with capacitor, unidirectional diodes, resistor, and LED connected to the output. Working principle of piezoelectric sensor. A piezoelectric transducer or sensor is a device that uses the piezoelectric effect to measure the change in acceleration, pressure, strain, temperature, or force by converting this energy into an electrical charge. A transducer can be anything that converts one form of energy to another. The piezoelectric material is one kind of transducer. When a force is applied on the piezoelectric material, it converts it into converts this energy into voltage. And when a electric charge is given to the piezoelectric sensor, it converts it into mechanical form. And this is called the actuator application. Working of the model. This is the simple block diagram of the working of the model. Here the piezo sensor converts the mechanical energy into electrical energy, and the unidirectional diode allows the flow of current in one direction. A battery stores the energy, and an inverter converts the one form of energy to another, that is like DC current to AC current, and a switch to complete or break the circuit, and the output in AC or DC loads. Rectifier circuit connection.
Bridge rectifier. Many electronic circuits require a rectified DC power supply to power various electronic basic components from the available AC main supply. Rectifiers are used to convert an AC power to a DC power. Among the rectifiers, the bridge rectifier is the most efficient rectifier circuit. We can define bridge rectifiers as a type of full wave rectifier that uses 4 or more diodes in a bridge circuit configuration to efficiently convert AC current to DC. The construction of the bridge rectifier. The bridge rectifier circuit is made of 4 diodes D1, D2, D3, D4 and the load resistor RL. The 4 diodes are connected in a closed loop. The input signal is applied across terminals A and B, and the output DC signal is obtained across the load resistor RL connected between the terminals C and D. The 4 diodes are arranged in such a way that only 2 diodes conduct the electricity during each half cycle.
Working of a rectifier circuit. When an AC signal is applied across the bridge rectifier, terminal A becomes positive during the positive half cycle while terminal B becomes negative. This results in diode D1, and D3 becoming forward biased, while D2 and D4 become reverse biased. The current flow in the positive half cycle is as shown in the figure. During the negative half cycle, terminal B becomes positive while terminal A becomes negative. This causes diodes D2 and D4 to become forward biased and diode D1 and D3 to become reverse biased. The current flow in the negative half cycle is as shown in figure. Model preparation. These are the steps followed to prepare the model. Bonding of PCT, soldering, connection, input and output of the rectifier circuit. Bonding of PCT is as follows. The bonding is done using a high strength epoxy. The resin and the hardener are taken in equal proportion and mixed thoroughly, as shown in the video. Care should be taken that both resin and hardener are taken in equal proportions. Mixing should be done thoroughly. The bonding of PZT should be done before the epoxy starts getting hardened. Thorough mixing should be ensured as shown to ensure a proper bonding. A thin layer of epoxy should be applied. As shown, a thin layer of epoxy is applied and the sensor is bonded onto the base. Soldering. Soldering is done as shown in the video. First, coaxial wires are taken and the ends of the wires are cut as shown. Then the piezo sensor plate is taken. Little flux is applied to ensure there are no impurities, and soldering is done. Care should be taken that the terminals are placed properly. Okay. In this way, soldering of all the PZTs is done. Now comes the connection part.
This is the circuit for footstep energy harvesting. The base chosen is a foam sheet upon which the PZTs are bonded. Soldering is done and secured using a epoxy protection coating. There are majorly two types of connections: series connections and parallel connection. In series connection, the voltage increases but the current flowing through all the components remains same. The PZTs give a voltage up to 5 to 7 volts, which is quite appreciable, but the current generated is quite less. So in order to generate more current, the PZTs are connected in parallel connection. This is the parallel, these are parallelly connected PZTs, and the N terminals are connected to the input of the rectifier circuit, and the output is connected to the LED.
Model testing. The model is tested as shown in the video. A dynamic pressure is applied on the PZTs, and it can be seen that electrical energy is generated, and it is shown by the glowing of the LED. Applying pressure to a piezoelectric material generates charge on its surface. In this state, the piezoelectric element behaves very much like a charged capacitor. It will discharge when connected to a load in a couple of milliseconds. In order to keep on extracting the electrical energy, one has to constantly reapply pressure to the material, that is to make it vibrate. This is why most of the times PZTs are used PZT devices are used to exploit sources of mechanical vibrations such as roadways, footsteps, raindrops. Using PZT patch for both structural health monitoring and energy harvesting in real-life structures is feasible. The same patch which scavenges energy during ideal period could be used for structural health monitoring as and when warranted. These are the references that I've followed. Thank you all for viewing.